Well, hello, ladies and gentlemen. Topics for today, we're going to review the concept of work and how to calculate boundary work, and this is from last lecture. And then we're going to move on to the other path function. Remember, we started off this chapter looking at path functions, or point functions, which are a function of the state of the system and not how the system got there. There are path functions, which are a function of how the system moves from one state to another. One of the path functions that we introduced last time was work. And in particular, we derived the expression for boundary work. And we did an example where we had to calculate the boundary work of a system. And today we're going to introduce a second path function, which is heat, or heat transfer Q. And we're going to go over the details of that. So topics today, we're going to look at heat transfer, how heat transfer is defined, what are the bases of heat transfer, the forms of heat transfer, how are they expressed? And then we're going to introduce quantities called specific heats. Specific heats tell us how a system's temperature changes. A system's temperature changes as we add heat. And as you might guess, the temperature change of a system depends on the path taken when we add the heat, because Q is a path function. So we're going to talk about specific heats. We're going to round off the lecture talking about specific heats, how they're defined, what they are a function of, and then we'll do an example involving specific heats, their application. All right? So let's review a little bit from last time. So we have boundary work. Boundary work, bound, and this is from, let's say, state 1 to state 2. So we have a system which moves, and I have a PV diagram, a pressure and volume diagram for the system. A system which moves from state 1 to state 2 along the path that you see here. The area underneath this curve represents the boundary work over the process 1 to 2. So W bound 1 to 2, that's the area underneath the PV curve. Mathematically, boundary work is defined as the integral of PdV as we go from volume 1 to volume 2 along the path 1 to 2, okay? So that's how boundary work is calculated. By the way, so the system is starting off with a certain volume, and let's say it's expanding. So our system here, I guess I'll stay down here. So our system is moving from state 1, so I have a pressure, I have a volume V1, I have a bunch of initial conditions here, and it goes to state 2. Let's say it's expanded a little bit from state 1 to state 2. So now I have a PV, pressure and volume at state 2. So it's expanded. The piston has moved upwards. So clearly the system, and I mean the system is the gas inside. So here's our system control volume, so the gas inside. So clearly the system has expanded. So it's done work because it's expanded against the weight applied by the piston, and there's a pressure inside. Because it's expanded, it's done work. So this quantity here, this integral here, is work done by the system. When the system does work, which is the integral of PdV, is positive. If you do work on the system, so if I'm squeezing it down instead of letting it expand, I'm doing work on the system, then the volume change is negative, and this integral will be negative. So if that integral is positive, work is being done on the system, by the system, work done by the system. If W is equal to PdV is positive, and if that integral is negative, that means you're doing work on the system, So work is positive when you're doing it, when the system is doing work, and it's negative when you're doing work on the system. So that's boundary work from last time. Let me show you some additional forms of work. There's not just boundary work, there's other forms of work. So other forms of work. Two kinds. Let's go over them one at a time. Actually, there are three kinds. We'll encounter the third kind a little bit later. There is shaft work. W shaft. So let's say we have a system and we have inside the system a little propeller. Okay? So there's a little propeller in here. And this propeller is spinning around. Okay? It's a propeller on a shaft and it's spinning around. Now, this shaft attached to the propeller is applied, this has a certain speed, so we have a certain angular velocity. Omega is angular speed, and that is in radians per second. So it's angular speed in radians per second. And there's also a torque applied at the shaft. There's tau, which is torque. Okay? There's tau, so we're applying a twisting force to the shaft. There's some resistance being encountered to spinning the shaft, and it spins at a certain speed. And the shaft work, or the rate in which shaft work is done, W dot shaft, which is a little bit of shaft work over a little bit of time. Little bit of shaft work, see the delta here? Delta shaft work over time is equal to the torque times the angular velocity, tau times omega. You multiply these two things together and you get power. So the shaft power, or shaft work per unit time, done by the system, is equal to the torque times the angular velocity. And you can see that, so torque times angular velocity, let's look at the units here. So torque, let's say, has a unit of, let's just do it in general. It has a length, L, times a force, F. So that gives me a torque, a length times a force. And then I have omega, which is unitless. It's radians per second, so that's unitless. And then I have time, t. So a length times a force divided by t, that has units of a length divided by time times a force. So this is a velocity. Velocity times a force. Velocity times a force. So torque times angular velocity gives me velocity times a force, which is power. Power. Work per unit time. work per unit time. So shaft power, W dot, is equal to the torque times the angular velocity, okay? So that is shaft power. Shaft power. Now there's another kind of work, or power if you like. And remember here we're talking about a mechanical transfer of energy. That's how we defined work in general, as a mechanical transfer of energy. There's also electric power. Electric power or work. If you like, work per unit time. Work per unit time. Electric power. So we have a system. So here's our system. And instead of having a shaft in there, instead of having a shaft, we have some wires. Okay, we have some wires here. Here we have a resistor, or I guess that looks more like an inductor. Okay, so we have a resistor here, R, and we have some current flowing through the wire. So we have some current flowing through the wire, through this resistor. So, and if you like, there is a voltage difference as a result of that across this resistor. So there is a delta voltage. It's a delta voltage across the wire or the resistor or the device that is dissipating energy caused due to the current flowing through the resistance. The electric power, W dot electric, is equal to the current times the voltage. So I times delta V. And remember, the definition here is the same as in the shaft power case. W dot electric, so I'm going to move this over. W dot electric is the little bit of electric work over a small period of time, and that is W dot electric, okay? So we've encountered now three forms of work, or power if you like. There's shaft work, there's boundary work, which has to do with the change in volume of the system. We have shaft work, which has to do with putting a little propeller or impeller into the system and spinning it. So we're adding energy to the system or receiving energy from the system by spinning the shaft. And the shaft power is equal to the torque times the angular velocity. So a little bit of work over a small amount of time, or a rate in which work is done. And then we have electric power. The rate at which electric work is done, W dot electric. W dot electric is I times delta V, the current times the volt drop across the resistor, okay? So three forms of work. Three forms of work. So that's work, ladies and gentlemen. That's work. We've done an example involving boundary work. If you go through and you look at your notes, you'll find that there's an example on shaft power. There's a problem that involves, I think it's boundary work and shaft power or electric power together. Or maybe that's later on. So just look through your notes. Talks a little bit more about shaft and electric power, okay? All right, let's move on to our next topic, which is our second path function called heat. So let's go over heat. Actually, let's take a short break here. Okay, so heat transfer. Heat transfer. Heat transfer is symbolized by the symbol Q. So what's the definition of heat transfer? So heat transfer is the transfer of energy between systems due to a temperature difference. Due to a temperature difference. So let's say I have two bars. Kind of like on the first day of lecture, we talked about, introduced the concept of heat transfer involving two bars that were in contact. Remember that from the first lecture? So we have bar A and we have bar B. And let's say TA is greater than TB. So this is the hot bar, and this is the cold bar, okay? So as a result of the temperature difference here, heat is going to be transferred from the hot to the cold bar. So we have heat transfer. And as far as A is concerned, so system A is the hot bar. As far as system A is concerned, QA is negative. So we have HT, heat transfer from A. So energy is flowing from A to B because A is hot, okay? So QA, heat transfer to system A is negative. Heat transfer is positive when it's to the system and negative when it's from the system, okay? Heat transfer is positive when it's to the system and negative from the system. Likewise, QB, heat transfer to system B, to system B is going to be positive. Why? Because we have heat transfer to system B, okay? So Q is positive to system, negative from system. Okay, the opposite of work. Remember boundary work? That was positive when energy left the system in the form of boundary work, or the system did work. Where heat transfer is positive when you're doing or adding heat to the system. So Q is positive when you're adding heat to the system, and is negative when heat or energy is leaving the system or you're extracting heat from the system. What about some notation here? What about some bases? What about some bases here? basis. So we have basis, we have expression, and then we'll talk about SI units. And English units for heat transfer, okay? Basis, overall process. Overall process. So that means Q from state 1 to state 2. That would be a way to symbolize heat transfer for some overall process. So we have a system which moves from state 1 to state 2 because we are adding a certain amount of heat, Q1 to 2, making the system hotter, increasing its volume, doing something, okay? An SI unit of energy, of heat transfer is energy, same units as energy. So we would have joules. And English units, we would have the BTU. BTU. All right. What about for a differential process? Differential process. That would be a little bit of heat transfer. Notice the lowercase delta there. Q is a path function, not a point function. So instead of writing dq, you write delta q, the Greek letter lowercase delta q, because heat is a path function. Units are energy. Okay? It's just a small process, a differential process. There's also the rate-based in other words, the rate in which heat transfer is done. That would be represented by Q dot, which is the little bit of heat transfer over a small amount or infinitesimal amount of time. So Q dot is equal to delta Q divided by dt. Time is a point function, so I put a d there. Heat is a path function, so I put a delta there. The units will be watts, which is a joule per second. So joule per second or a watt. Or a watt, joule per second or a watt. And then we have horsepower for the English unit. You can also write this heat transfer per unit mass. So there's also, I don't know, overall per unit mass. I could do that. That would be Q divided by the mass of the system, or lowercase q, Okay? You can write 1 to 2 on there if you want. And that, of course, would have units of joule per kilogram and SI, and BTU per slug or something. Pound mass. Okay? If I knew the mass of the system, then I could divide the heat transfer by the mass and I'd get heat transfer per unit mass. Sometimes that's an interesting way to look at heat transfer per unit mass. Okay? So these are the various bases or ways that we can express heat transfer along with their units and the symbols used to represent them. By the way, the same thing can be said for work. I didn't draw this table for work, but you could replace everything in here, every Q in here with a W. Work for an overall process, W1 to 2. Differential work, del W. Rate work over a certain work on a rate basis. So that would be W dot, del W over dt. And then we'd have lowercase w, which would be the work over the process divided by the mass of the system. So I can rewrite this, make this entire chart by substituting work for Q. Substituting work for Q. Okay, so we can do the same thing with work. All right, so heat transfer. Heat transfer is the transfer of energy between systems due to a temperature difference. Heat naturally flows from hot systems to cold systems. Heat transfer is positive when energy is being added to the system, and is negative when energy is flowing out or being extracted from the system. And then we have the various bases for heat transfer or work. You could do this whole table with work as well. All right? Okay, let's move on to the next topic here. Let's actually start getting into more detail on heat here. This has just been a bunch of qualitative stuff. Just been a bunch of qualitative stuff. Now, why do we add heat to a system? Well, one of the reasons we add heat to a system, probably the most relevant reason we add heat to a system, as far as everyday lives are concerned, is to increase the temperature. You add heat to a pot of water, and you raise it up to the boiling temperature, and you make your tea, or your coffee, or you boil your potatoes. Okay, so that's one of the most fundamental applications of heat transfer, to raise the temperature of a substance. Let's look at adding heat to a system for two different paths or processes. And the topic here we're going to be leading into is called specific heats. Specific heats. So let's say I have a container here, a piston cylinder device, in fact. And I have some sort of mass in here, some sort of material with a certain mass. And it starts off with a temperature T1. So this is state 1. And now I'm going to add heat. Q 1 to 2. Q 1 to 2. I'm going to add some heat. In fact, I'm going to add a very small amount of heat, a differential amount of heat, very small amount of heat. Del Q. Let's add a little bit of heat. In fact, I'm going to get rid of this 1 to 2 right here. I'm just going to leave del Q, just for notations purposes. So we're going to add a little bit of heat. And so presumably the system expands ever so slightly. So the piston is now moved up because the system has expanded a little bit. And now I'm at a temperature T2. So this is my state 2. All right? And by the way, what's state 2? What's temperature at state 2? The temperature at state 2 is equal to the temperature at state 1 plus the differential change in temperature. So T2 is T1 plus a differential, dt, differential change in temperature. So I add a differential amount of heat, infinitesimal amount of heat, del Q, and it warms up the system by an amount dt. Small heat transfer results in a small temperature rise. Now, let's define specific heat at constant pressure. I'm in a piston cylinder device here. This is a piston cylinder device, so I'm going to make this an isobaric process. What's isobaric mean? Constant pressure. Baric, iso, constant pressure. I'm going to define the specific heat at constant pressure. Cp equals specific heat at constant pressure. Specific heat at constant pressure, Cp. How's it mathematically defined? Take the amount of heat I've added, del Q, divide it by the mass of my system, m, and the temperature change, dt. Cp is equal to del Q over m dt for a constant pressure process. Constant pressure process, del Q over m dt. If you like, specific heat is the amount of heat required to raise the temperature of the system by 1 degree per unit mass. The amount of heat required to raise the temperature of the system by 1 degree per unit mass. Cp equals del Q over m dt for a constant pressure process. Put a box around it. That is the definition of specific heat, constant pressure. What's the units of this? What are the units of this? Well, in metric, well, in anything, I guess energy per unit mass per degree. Hence, Cp is the energy required per unit mass per degree for a system. Okay, so that's Cp. There is another specific heat. Remember, heat is path dependent. So specific heat will be different depending on the path. That quantity, del Q over m dt, will be different depending on the path taken. For a constant pressure process, we let Cp equal to del Q over m dt for a constant pressure process. What about if instead we have a rigid container? A rigid container. So we have a certain amount of mass in here and we have a T1. And this is a rigid container, so volume is constant, a rigid container. So I add heat to my substance in this rigid container, Q. It's a differential process, so I'm adding del Q, and I end up at state 2 with a temperature T2 is equal to T1 plus dt. Okay, same thing as before, except we have a constant volume process. Isochoric process. What's isochoric? Constant volume. Constant volume. So we have a new specific heat defined because the path is now different. Instead of traveling an isobaric process, we're now transversing an isochoric process. CV, constant volume, not constant pressure. CV is equal to del Q over M dt for a constant volume process. Specific heat at constant volume. Specific heat at constant volume. At constant volume. So put a box around this. You need to know the definition of specific heat. You need to know the definition of specific heat, both for constant volume and constant pressure. So you need to know this. Units for this are energy per unit mass per degree, or if you like, the amount of energy required to heat up 1 kilogram of the substance, 1 degree for a constant volume process. That's what CD, the number, represents. Okay? All right. Let's talk for a minute here about, oops. There we go. Let's talk for a minute here about how you calculate specific heats, and then we'll move on and do an example. So how do you calculate specific heats? In fact, I'm going to write them right over here. So specific heat at constant pressure is the little bit of heat added per unit mass per degree change. And then we have, and this is for constant pressure. And then we have CV, which is the little bit of heat added per unit mass per degree change for volume equals constant. Okay, constant volume. Let's put a little box around these. These are going to be important. We're going to be using them. Hell, we're going to be using them throughout the semester. Now, the first thing I want to point out is that CP is typically greater than CV, for almost all applications. So why would specific heat at constant pressure be greater than specific heat at constant volume? Let's put the picture up again. Let's put the pictures up again. We have our isobaric process. So heat is being added, and if it's isobaric, that means that the piston has moved upwards. Here's our system. So we're adding heat. Let's say we're going from state 1 to state 2. And I have a temperature T1 and I have a temperature T2. Okay? So that's the constant pressure process. And then we have the constant volume process, which involves a rigid container. So we're going from state 1 to state 2, and we're adding heat Q1 to 2. And I have a temperature T2 and a T1. So why might these temperature differences, T1 and T2, why might the heat transfers be different? Why might the heat transfers be different, required to affect the same change in temperature for a constant pressure versus a constant volume process? If I'm going to raise the temperature of both these systems by 1 degree, and they both have the same mass, let's say, why do I have to add more heat for the constant pressure versus the constant volume process? Well, the reason is because here in the constant pressure process, boundary work is being done. The system is expanding. So some of the heat is being used not only to heat up the system to produce a temperature change, but to expand the system. We're doing boundary work for the isobaric process, whereas the isochoric process has no boundary work. No work bound, and in this case, work bound is greater than 0, okay? So that implies that Cp, the amount of heat to raise the temperature of the material, let's say by 1 degree, is greater for a constant pressure process than for a constant volume process. So this is due to presence of boundary work for isobaric process, due to presence of boundary work for the isobaric process. All right? Another thing to notice about specific heat. Let me tell you a few more odds and ends about specific heat. And we're going to be coming back to this stuff later, but I'm just kind of trying to whet your appetite. So if you see this, it'll jog your memory when you see it the second time. You'll be seeing some of this information the first time now, and I will be proving it to you later on. So another little fact about specific heat. Cp is equal to Cv. Specific heat at constant pressure and specific heat at constant volume are equal to each other for solids and liquids. Cp and Cv are equal to each other for solids and liquids. Why might that be the case, given what we just discussed? Is a solid compressible? Does the volume change in a solid when we raise or lower its temperature? Does it change a lot? Let's say nearly as much as a gas. And the answer is no. Solids are essentially incompressible. They do expand a little bit, very small amount when you heat them up, but nothing compared to a gas. Nothing compared to a gas. Same thing for a liquid. Liquids do expand or contract slightly with temperature, but nothing compared to a gas. So specific heat at constant volume and specific heat at constant pressure are approximately equal to each other for solids and liquids. They're exactly equal to each other for incompressible substances. Okay? No boundary work possible for incompressibles. A gas is not incompressible. Liquids and solids are approximately incompressible. If you want to be absolutely strict here, just put approximately equal if it makes you feel a little bit better. Okay, so Cp and Cv are the same for liquids and solids. So that's another fact. Ideal gas. Let's say we have an ideal gas. Ideal gases. Let's look at what we can say about, what we will be saying about Cp and Cv for ideal gases. In general, specific heats are a function of two things, temperature and pressure. These specific heats, the numbers that you look up in tables, for particular substances, they tend to vary with temperature and pressure. In fact, let me state that right now. Note, Cp is a function typically of temperature and some other stuff. Typically a temperature and a pressure, a temperature and a volume, something. So Cv is a function of temperature and some other stuff. A temperature and a pressure, a temperature and a volume. So there are tables for specific heats, and they're typically functions of temperature and or pressure, okay? But for ideal gases, specific heats are a function of temperature alone. Cp is a function of temperature alone, and Cv is a function of temperature alone. Why is that? Because we already have an expression that relates pressure, temperature, and volume, the ideal gas law. So in theory, we can solve for one or the other and reduce a two-variable dependence into a single variable dependence because we have the ideal gas law. So in general specific heat, Cp and Cv for ideal gas behavior is a function of temperature alone. And these Cp's and Cv's are tabulated, as you will see soon. All right? Okay, so let's do an example here. Let's go through and do an example. Okay, before we get started here, I actually realized that I forgot, there was one more thing I was going to say about specific heat when we can assume ideal gas behavior. One other little thing besides specific heats are a function of temperature alone. There's a relationship between Cp and Cv that holds only for ideal gases. Cp is equal to Cv plus the gas constant R. Okay? So the relationship between Cp and Cv, the difference between Cp and Cv is the gas constant R. I want you to accept this for the moment. Just accept this for the moment and I will prove it later. It has something to do with this boundary work that is the distinction between Cp and Cv. You can actually calculate the boundary work and therefore for an ideal gas and therefore get this expression Cp is equal to Cv plus R. But for the time being, I think you should commit it to memory that for ideal gases, the difference between Cp and Cv is the gas constant. Okay? All right, let's move on and do an example here. Let's do a nice simple example to get our feet wet. We have a rigid container containing air, a mixture of nitrogen and oxygen, air. Initially, this system starts off at a temperature T1, and then we add heat, Q1 to 2, and we heat the system up to T2. T1 is equal to 300 degrees Kelvin. T2 is equal to 600 degrees Kelvin. I want to know how much heat is required per unit mass, lowercase q. How much heat is required per unit mass, Q divided by M, to raise the temperature of this air contained in a rigid container from 300 to 600 degrees Kelvin. I want to know how much heat is required. Okay? All right, so how are we going to proceed here? Well, we're talking about specific heats, so we better use specific heats. We are, after all, on Chapter 3, which is specific heats and energy interactions, so analysis. Let's write down the definition of specific heat. Which one? Cp or Cv? What process is this? We're adding heat from state 1 to state 2. What kind of process is this? Rigid container? Well, that means presumably constant volume. Isochoric process. Isochoric process, volume is constant. So let's write down the definition of CV. CV is equal to the little bit of heat transfer divided by the mass of the system divided by the temperature change due to that little bit of heat transfer. Let's solve this for Q. Little bit of Q. Del Q is equal to CV m dt. Okay, so all I did is I solved for del Q. Now, del Q is an infinitesimal or differential heat transfer. I want to get the total heat transfer per unit process from state 1 to state 2. So I think the second thing I'm going to do is I'm going to divide both sides by the mass of the system. If I divide both sides of the equation by the mass of the system, the del uppercase Q becomes a del lowercase q. Del lowercase q. So I have del lowercase q is equal to, the m's cancel out, and I get CV dt, all right? Now I want to get the overall heat transfer lowercase q1 to 2 per unit mass. How do I go from a differential process involving del's and d's to an overall process? I have to integrate. Let's integrate this thing over the process. 1 to 2. Temperature, dt, is the, well, variable of integration is T. So I'm going from T1 to T2 here, okay? The quantity on the left is going to be the overall heat transfer per unit mass, Q1 to 2. So I end up with Q1 to 2 is equal to the integral of CV dt. Now what do? We need to integrate this. If I knew the functional form of CV, I could integrate with respect to temperature. I don't know a lot about CV at this point. And remember, we're integrating from T1 to T2. Air in a container. Maybe I can assume ideal gas behavior, and then maybe CV is a function of temperature alone, and then maybe I can show you some tables to extract out CV, okay? And we can perhaps integrate this integral. Let's see if the ideal gas equation or ideal gas behavior is valid for our air. Let's see if the ideal gas law is valid for our air. So T reduced. Remember, ideal gas law is valid when T reduced is greater than 2. So the lowest T reduced value is 300 K. T reduced min is equal to T1 over T crit. So what's the critical? Let me do a share here. What is the critical temperature for air? I thought it was like 1, oops. So what? Air, 133 Kelvin. 133 Kelvin. So I have 300 degrees Kelvin divided by 133 degrees Kelvin. And that's about 2 point something. 2.25. 2.25, which is greater than 2. I don't know anything about the pressure. Critical pressure is pretty darn low for air. I'm sorry, high for air. So if you look here, if you look, (37.7 bar). So reduced tip pressure need to be about 0.2 or less. So because the critical pressure is so high, for most workable pressures, I would say it's quite plausible from an engineering standpoint that our reduced pressure is going to be less than 0.2. So I'm not going to make too much of a song and dance out of it. I'm just going to write here under my assumptions, I, G, B, valid. We can treat the air as an ideal gas, IGB valid, okay? And therefore, CV is a function of temperature alone, and so CP, but we're interested in CV. Function of temperature alone. Okay, so CV is a function of temperature alone now. It is a function of temperature. So what is CV? It varies with temperature. It's a function of temperature. Let's have a look at some values of CV here for air. Okay, so let's go back to the appendix here and let's look and see if we can find specific heats, a table of specific heats. Table B8. Here's specific heats for solids and liquids. Remember CP and CV were the same for solids and liquids, in other words, incompressibles. So here we have CP values as a function of various temperatures. So CP and CV typically vary with temperature, and other stuff for solids and liquids, they're a function of temperature. And they're the same, CP and CV are the same. And now we have ideal gas specific heats, various gases. Air, temperature, CP, CV. At 300 degrees Kelvin, CV is 0.718 kilojoule per kilogram degree in Kelvin. 600 degrees, 0.764 kilojoule per kilogram degree in Kelvin. Okay? So specific heats over our process as the system heats up from 3 to 600 is changing a little bit. It's going up by about 0.06, 0.05. It's increasing by about 10% as the system heats up. So CV is not entirely constant during the heating process. It's getting bigger as temperature goes up. So what are we going to do? We're going to evaluate our specific heat at the average temperature, 450 degrees Kelvin. So what we're going to do is the following. This integral is approximately equal to CV evaluated at an average temperature. What's the average temperature? It's 600 plus 300 divided by 2. That's Kelvin, or 450 degrees Kelvin. Okay? What can I do with a constant or average specific heat? What can I do with it when it's in an integral? This guy is now a constant value evaluated, CV evaluated at 400 degrees. Let's pull it out of the integral. CV T average evaluated, that's 450, times the integral of dt from T1, running out of space here. dt from T1 to T2. Integral dt from T1 to T2 is delta t. So I get CV evaluated at 450 degrees Kelvin. Delta t, or if you like, CV evaluated at 450. T2 minus T1. Okay, so the heat transfer. Let's write that down over here so we can start fresh. The heat transfer per unit mass over the process, Q1 to 2 is equal to CV evaluated at the average temperature, which is 400 degrees Kelvin, times T2 minus T1. Now, we've chosen to average the specific heat, so maybe we better put that in our assumptions. CV is equal to CV at T average. Okay? So we're going to evaluate the specific heat, make it a constant so we can pull it out of the integral, and evaluate it at the average temperature. Okay? Let's see here. Let us get the value. CV at, for air at 450 degrees is 0.733. .733, and that has units of kilojoule per kilogram degree in Kelvin. And my temperature change is 600 minus 300, T2 minus T1. So we have 600 minus 300, and that all has units of degrees Kelvin. Notice the Kelvins cancel out. The specific heat and the temperature change. And I get 0.733 times 300. $219.9 kilojoules per kilogram. 219.9 kilojoule. Oh. Sorry about that. There we go. 0.733 kilojoule per kilogram degree in Kelvin. Our temperature T2 was 600 degrees. Our temperature T1 was 300. How much heat to raise the system from 3 to 600 degrees? 219.9 kilojoules per kilogram. Notice the Kelvins cancel out. So Q, lowercase q, Q1 to 2, which is the heat transfer from state 1 to state 2 per unit mass, is equal to 219.9 kilojoules per kilogram. Box it up. Done. Over. First use of specific heats in a problem. How to calculate the heat transfer to heat up air over an isochoric process. Okay? Now, one little thing I want to point out before we move on, because you will have an opportunity to do this kind of a problem in a slightly different way. We assumed constant specific heat to do this problem. So we assumed a constant specific heat, a specific heat evaluated at the average temperature, so that we could pull it out of the integral and evaluate the integral to get the heat transfer. That's why we assume constant specific heat. And if you looked at the tabulated values for specific heat, they don't change that much. So here, let's go back and look. Specific heats for constant volume process, again, 0.721, 0.776. about a 0.055 kilojoule per kilogram degree Kelvin change, about 10% variation between 300 and 600 degrees, about 10% or less. So we would expect our heat transfer calculation to be within 90–95% accuracy. What if you want very, very good accuracy for your calculation? Let's say you want maximum accuracy. Well, look at this. Table B9. Ideal gas polynomial expressions for specific heat. Cp over R. So this is a dimensionless quantity. Remember, universal gas constant, the gas constant R, had units of kilojoules per kilogram degree Kelvin. So does specific heat. So Cp over R is dimensionless. Cp over R for various ideal gases can be expressed in a fourth order polynomial with coefficients alpha, beta, gamma, delta, and epsilon for the coefficients. I could have done this problem. I'm not going to. I'm going to leave it for you to do it for a homework assignment. I could have done this problem by substituting this polynomial expression into my integral and then integrated. Okay, I could have integrated. The values for the coefficients, alpha through epsilon, are given by these columns here. Note, for the various gases, here's air. Alpha is 3.653 for this polynomial curve fit for specific heat, Cp. Beta, negative 1.337 times 10 to the negative 3. So beta times 10 to the 3 is this value. Gamma, this value times 10 to the negative 6. Delta, this value times 10 to the negative 9. So all these coefficients get progressively smaller by 3 orders of magnitude as you move up in order in the polynomial. Okay? So another way to do this using variable specific heats by the equation in table B9 is to substitute this expression into your polynomial, into your integral, and integrate with respect to temperature. Plug in the various temperatures, plug in the various coefficients, and you get the heat transfer. You'll have a homework assignment involving comparing a constant specific heat versus a variable specific heat using these polynomials for a heat transfer calculation. All right, ladies and gentlemen, I think that's all I'm going to say today. I think we've done enough. We're going to move on to the first law of thermodynamics. In other words, the energy balance. We'll make it a short lecture for Wednesday, given this is a little bit longer lecture. We'll finish up on, we finished up heat and work. We're going to move on to the energy balance tomorrow. Take care, ladies and gentlemen.